Well, this is QOD number 43, and we are going to talk about buffers. And we've talked about buffers already sort of informally, but I wanted to do a formal treatment of the topic of buffers. And so here are some examples of some chemical buffers. These are actually used for calibrating a pH meter. You have a pH 10 buffer, a pH 4 buffer, and a pH 7 buffer. We'll talk a little bit more about how you might get to that a little bit later on in the video. We are not talking about this sort of buffer, so we can rule that out. We're talking about chemical buffers. So really what I'm dividing this talk into is two parts. What does a buffer consist of, which we have already talked about to a certain extent in class in talking about the Henderson-Hasselbalch equation and the common ion effect and titration curves. And so we'll go back over again as what actually is it that you have in a buffer solution, and then more to the point really of what most of this presentation is. What does a buffer do and how does it do it? And so what is the composition of a buffer? Well, we've mentioned this before. It is a solution, an aqueous solution that contains a weak acid and its conjugate base, or vice versa. That is a weak base and its conjugate acid. And you'll remember we've said this before in chapter 16, that we define a weak acid as being an acid whose Ka value is less than 1 and greater than 10 to the minus 14th. That would be a weak acid. And if you'll recall also from chapter 16, that there's a relationship for any conjugate acid-base pair, there's a relationship between Ka and Kb. And since Ka times Kb is equal to 10 to the minus 14th, then it follows mathematically that if the Ka of your weak acid is between 1 and 10 to the minus 14th, then the Kb of its conjugate base is also going to be between 1 and 10 to the minus 14th. And that's why when we were binning acids and bases back in chapter 16 by negligible versus weak versus strong, we said that the conjugate base of a weak acid is a weak base. Because if your Ka is between 1 and 10 to the minus 14th, then the Kb of your conjugate partner is also going to be between 1 and 10 to the minus 14th, and that makes it weak as well. So anytime you have a weak acid and its conjugate base, or a weak base and its conjugate acid, you have two weak species. And so a buffer solution always then is going to contain both a weak acid and a weak base. And so here's the sort of question you might get on a QOD or on a quiz or a test or even the AP exam, which is, here's a list of 5 combinations, and the question is which, if any, of the following would be a buffer. And so in each case, I have an acid and its conjugate base. So I've got acetic acid with its conjugate base, acetate, hydrochloric acid with its conjugate base, chloride, ammonium and its conjugate base, ammonia, hydronium and its conjugate base, water, and then another weak acid, weak base pair, but they're not a conjugate pair, hydrofluoric acid and the nitrite anion. So which of these 5, if any, would comprise a buffer? And so the answer is the 2 that I've got highlighted here, because this is a conjugate acid-base pair and they are a weak pair. Acetic acid is a weak acid, acetate is a weak base. This would not be a buffer because hydrochloric acid is a strong acid. Its K value is much greater than 1, which conversely means that the Kb value of chloride is much, much less than 10 to the minus 14th. So that is not a weak acid-base pair. That is not a buffer. Ammonium and ammonia is a weak base, and therefore its conjugate acid, ammonium, is a weak acid. Hydronium and water is not a buffer system, although they are a conjugate acid-base pair. For one thing, this is the solvent for buffer systems, water, but also hydronium is a strong acid, and so that would not qualify as a buffer. Here we have a weak base and a weak acid, but they are not a conjugate pair. And so therefore they are not that would not make a buffer. And we won't really have time in this class to talk about what would happen if you had this combination, but it would not be a buffer. We're going to focus for the most part in the rest of this video on one specific buffer system, which would be a buffer made up of formic acid and sodium formate. And just as a reminder, we've talked about the fact that sodium is always simply there as a counter ion or spectator ion to get the anion into solution. So when we say sodium formate, we really mean sodium ions plus formate ions, and therefore your buffer is a buffer of formic acid and formate. That would be true of anything here when you were if you were trying to get these things into solution. You'll notice that in each one of these pairs, something is charged either positively or negatively. You would make this buffer by combining acetic acid with sodium acetate. You would make this buffer by combining ammonia with ammonium chloride, etc. Okay, well, let's talk. So we've talked about what a buffer is in terms of what it's chemically composed of. What does a buffer do? Buffers are called buffers because they resist changes in pH. And so what we mean by that is that if we add a little bit of strong acid to the buffer, it only causes the pH to go down by a little bit. Or if we add some strong base to the buffer, it only causes the pH to go up by just a little bit. And we'll talk about the mechanism of that in just a moment. There are many important buffers that occur in nature, and life really couldn't go on without them, most specifically to the buffering of your blood. And so blood maintains a pH right around 7.4, and that's because it is buffered. And the buffer that maintains your blood at that pH is a combination of a couple of things: carbonic acid and bicarbonate, as well as a combination of dihydrogen phosphate and monohydrogen phosphate. There are other examples of buffering in nature. Lakes, bodies of water that are adjacent to limestone rock. Limestone is calcium carbonate. They are buffered by a combination of bicarbonate and carbonate. And what that does is, if you've got a lake that is buffered in that way, it's resisted to acid rain. And so there are some instances of acid rain killing off living things in lake, like fish and other organisms. And but if you have a lake that's buffered by this bicarbonate carbonate buffer, then you have a system that is resistant to pH changes from acid rain. So let's go back to our formic acid formate buffer, and let's just compare what would happen if we took pure water and added a little bit of acid or a little bit of base to it, versus taking a buffer and adding a little bit of acid or a little bit of base to it. If I take a liter of just pure water, and here I've just indicated that if I have a liter of pure water, it's going to have a pH of 7. Here's my little handheld pH meter. If I add just 0.02 moles of hydrochloric acid to that, so I'm making a 0.02 molar hydrochloric acid solution in water, that pH is going to go down a lot. It's going to go down from 7 to 1.7, because 1.7 is the negative log of 0.02, which you'd have a 0.02 molar solution. If I add 0.02 moles of sodium hydroxide to pure water, the opposite thing's going to happen. The pH is going to shoot up, because the negative log of, you'd have a 0.02 molar solution of hydroxide. The negative log of that is 1.7, which would be the pOH. Therefore, the pH would be 12.3. And so addition of just tiny amounts of strong acid or strong base to pure water is going to deflect its pH by tremendous amounts. Now, what happens if we do that with a buffer? If I make a buffer of formic acid and formate, and let's say it's 0.5 molar in each species, so 0.5 molar in formic acid, 0.5 molar in formate. If I do, that's going to start with an initial pH of 3.74. If I add 0.02 moles of HCl, the pH is going to go down, but it's not going to go down by 5 log units like it did with the pure water. It only goes down from 3.74 to 3.70. And if I add 0.02 moles of sodium hydroxide to that, again, the pH will go up, but rather than going up by more than 5 log units, it's only going to go up from 3.74 to 3.77. So how do buffers do this? How do buffers have this magic ability to keep pHs from changing very much? Well, we saw a little bit of this when we were doing titration curves, but let's just think about this in terms of chemistry. A buffer, as we have said, contains both a weak acid and a weak base. And therefore, if I add any strong base to that solution, it's simply going to react with the weak acid and essentially turn that strong base into water. And I'll show you what I mean by this in just a second. Conversely, if I added strong acid to that buffer solution, it would simply react with the weak base to convert that strong acid into water and weak acid. So let's look at some examples. Again, let's consider our formic acid formate buffer. If I added strong base to this buffer system in the form of hydroxide, it will react with the formic acid to form formate plus water. Then let's just go back and look at this like we did back in chapter 16 and trying to figure out where the equilibrium lies in an equation like this. In this particular reaction, formic acid is the acid on the reactant side, hydroxide is the base on the reactant side, formate is the base on the product side, and water is the acid on the product side. Formic acid with a Ka of 10 to the minus 4th is a much stronger acid than water, which has a Ka of 10 to the minus 14. Therefore, this is the strong acid and that's the weak acid. Therefore, this is the stronger base and this is the weaker base. And therefore, this equilibrium is going to lie very heavily on the side of products. If I add hydroxide to this buffer, it's essentially all going to react with formic acid to destroy the hydroxide, react it away, convert it into water, and at the same time, I'm converting formic acid into formate. The reverse is also true. If I add strong acid to this buffer, which would come in the form of hydronium, it's going to react with the weak base, the formate, to convert that into formic acid and convert the formate, the hydronium, into water. Once again, I can define which is the base and which is the acid on either side, and then I can compare them. Hydronium is a much stronger acid than formic acid, so this is the strong side, this is the weak side. This equilibrium is going to very strongly favor products. And so if I add strong acid, it will also disappear because it will react away. Let me show you this to you in a more graphical looking form. And once again, this is just to show the weak acid is going to react with any strong base we add. The weak base is going to react with any strong acid that we add. Here's our initial buffer, and not every buffer has to contain the HA and A minus in equal amounts, but it's always useful just for the sake of the thought experiment to think about it being that, starting with equal amounts of both. If I add hydroxide, it'll do what I just showed you on the previous slide. The hydroxide will react with the formic acid to give me now less formic acid and more formate, but crucially, all the hydroxide is gone. After I added hydroxide, it simply reacted with the strong acid. And so now I don't have, the ratio of the two is not the same as it is here, and so the pH will change a little bit, but fundamentally what I still have is a solution of a weak acid and a weak base with none of the hydroxide left. And if I add hydronium or H plus to that, it's going to do the same thing. It's going to react with the formic acid. It's going to react with some of the formate to convert it into formic acid. But crucially, it'll react all the hydronium away. And so when that happens, it simply reacts to give me a new combination of formic acid and formate. Let's talk real quickly before we do a problem about what's called the pH range. Essentially, the pH range of a buffer is the range of pH values over which it works effectively, and that turns out to be about 1 log unit on either side of the pKa. Remember that because of the Henderson-Hasselbalch equation, when the base concentration and the acid concentration, that is when the HA and the A minus concentrations are the same, then pH is equal to pKa. And so if we go back to this picture, in this situation, the pH of this buffer would be equal to the pKa. It's pretty much good for 1 log unit on either side, because once you go more than 1 log unit on either side, that means the ratio of A minus to HA is greater than 10 or less than 1/10, and you're nearing the edge of that buffer region and where it's going to be useful. So you really want to pick a buffer system that has a pKa within 1 log unit of the pH, the desired pH that you want. And so here are some typical buffer systems we might consider using. Acetic acid acetate, bicarbonate carbonate, dihydrogen phosphate, monohydrogen phosphate, monohydrogen phosphate, phosphate. In each of these cases, we've got a combination of a weak acid and its conjugate base. And we have a list of K values here for each of these weak acids. And so if we go on and calculate the pKa for each of these, that really gives us the reasonable range of what sort of a range of pHs could we use that buffer in. And so we could make an acetate acetic acid buffer to cover a range between, say, 4 and 6, pH around between 4 and 6. Bicarbonate carbonate to make a buffer that would cover in a range between, say, 9 and 11. Dihydrogen phosphate, monohydrogen phosphate would give you a buffer that would operate from, say, 6 to 8. And the hydrogen phosphate phosphate would give you a buffer that would operate between, say, 12 and 14. That's a really high pH to tend to buffer something in. We tend to want to buffer things in the ranges of like between 3 and 11 or 3 and 10 or something like that. This is not a typical buffer system that you would use. All right, so what's going to happen? How do we do the calculation to figure out, A, what the initial pH is of our buffer, and then what the pH would be after we had added some quantity of strong acid or strong base to it? Well, what we're going to do is first figure out how many moles of HA and A minus we have. We can plug that into the Henderson-Hasselbalch equation. That'll tell us our initial pH. If we add strong acid or strong base, we can use an ICE table or an ICF table to figure out what the new concentrations or numbers of moles of HA and A minus are. Once we know that, we can apply the Henderson-Hasselbalch equation to tell us the pH. So let's try that. So let's just, to summarize what I just said, determine the number of moles of HA and A minus to begin with. That would tell you your beginning pH of the buffer. Use an ICF table, and now I'm using F instead of E because we're talking about generally a reaction that goes to completion. So it's initial, change, and final. Use an ICF table to determine the moles of HA and A minus after I add a little bit of a strong acid or a strong base. And then use Henderson-Hasselbalch to determine the new pH. So here comes our problem. A buffer is made by adding 0.3 moles of formic acid and 0.3 moles of sodium formate to enough water to make 1 liter of solution. So it is 0.3 molar in each, but we can just as easily talk about it being 0.3 moles of each. The initial pH of the buffer is 3.74, and we'll talk in a second about how we got that. Calculate the pH of this solution after 0.02 moles of sodium hydroxide has been added. All right, well, the initial pH, because the concentrations of formic acid and formate are the same, that puts us in the situation where the pH is equal to the pKa. And therefore, the pH is going to be equal to the negative log of 1.8 times 10 to the minus 4th, which is 3.74. So that's our initial pH. Now I can construct my ICF table. Remember, we had 0.3 moles to begin with of both the formic acid and the formate, and I'm adding 0.02 moles of hydroxide. So here's my reaction. Here are all of my reactants. All of these coefficients are 1, and therefore this is going to be minus x, and plus x. I clearly have a limiting reactant here, and because all the coefficients are 1, it's simply going to be the thing that I have the fewest moles of. So x becomes 0.02. And so I can simply write that in, X being 0.02, and therefore I can calculate the final moles of each. Once more, because the equilibrium here lies so thoroughly on the right that we can simply write this as a one-directional arrow. We'll have no hydroxide left when we're done. We will have 0.02 moles of formic acid, less than when we began. We will have 0.02 moles of formate, more than when we began. And now we can take those values and plug them into Henderson-Hasselbalch. 3.74 plus the log of 0.32 over 0.28. That's a misprint. That should be 0.280, not 0.200. That's 3.74 plus 0.06, and therefore the pH is going to be 3.8. Does that make sense? Yeah, we added a little bit of hydroxide, therefore we expect the pH to go up. Again, that's 0.280, not 0.200. And so the pH goes up to 3.8. So there's a typical problem. That's the end of our video. I will give some suggested problems for the QOD and look forward to seeing you, and thanks for watching.